I'm Norihisa Usui from Meteorological Research Institute of Japan Meteorological Agency. Today I'm going to talk about improvement of the ocean 4D scheme for high accuracy sea surface temperature analysis and forecast. Sea surface temperature (SST) is one of the essential ocean variables. It plays a crucial role in heat, freshwater, and momentum exchange at the ocean-atmosphere interface. Now there are various SST products based on satellite and/or in-situ observations. Their temporal and spatial resolutions are typically daily and a quarter degree. The SST products are generally produced by objective analysis methods such as optimal interpolation. And in many ocean data accumulation systems, such gridded data are utilized for accumulation. However, it is desirable for high-resolution systems to accumulate satellite level 2 data directly because gridded SSTs are spatially and temporally smoothed. JMA has been operating a 4D system, Move 4D based on an eddy resolving model for the North Pacific. In this system, JMA's SST product, MGD-SST, with a resolution of 0.25 degree is used for data accumulation with 10-day accumulation window. Here we compare SST field between MGD-SST on the left and Move 4D analysis field on the right. As shown here, you see that MGD-SST is spatially and temporally smoothed. That's why in this system, temporal mean SST averaged over the 10-day accumulation window is used for data accumulation. So short-term variations of SST are not forced by MGD-SST. So it is a challenging issue to analyze short-term variation of SST with the present 10-day accumulation window. To address this issue, in this study, the present 4D scheme in MOVE is extended to reproduce detailed spatial and temporal variations of SST with the present setting of the 10-day accumulation window. And accumulation experiments with high-resolution satellite SST are conducted, and the impacts of the new 4D scheme are evaluated. So first I explain the present 4D scheme in the MOVE system. This is the cost function used in the present 4D. The first term represents the background term, and the second term is the observation term. And we optimize temperature and salinity increments to the initial condition within the accumulation window by minimizing this function. In this 4D algorithm, initialization scheme of incremental analysis update IAU is incorporated. This correction term in the model equation represents the IAU initialization term. Although the velocity field is not directly optimized in this system, it is corrected according to the geostrophic adjustment during the IAU period. Because the typical timescale of the geostrophic adjustment in the mid-latitude is about 1 day, the IAU initialization period is set to 3 days in our system. So in the newly developed 4D scheme, the control variable is extended to include daily SST increments like this. in order to represent detailed spatial and temporal SST variations. And we assume that errors of the daily SST are independent from the temperature and salinity increments to the initial condition. So the background error covariance matrix B is represented by this block diagonal matrix. And the background term for SST is added to the cost function like this. So this Fodiva scheme can be regarded as a kind of weak constraint Fodiva. So, we implemented this scheme into our Fodiva system and conducted assimilation experiments. In the experiment, we assimilate high-resolution SST derived from the Himawari 8 satellite. Himawari 8 is a geostationary meteorological satellite launched in 2014. It is located at 140 degrees east at the equator, and it covers this region, this area. And the infrared sensors of Himawari observe skin SSD every 10 minutes with a resolution of 2 km. So it should be noted that the skin SSD represents water temperature typically at 10 micrometer depths, while the first layer of our assimilation model is located at 1 meter depth. And the model SST represents so-called bulk SST. So we need some correction to Himawari SST before data assimilation. In this study, to correct the Himawari SST, we created a bias table every 2-degree box as a function of local time and mass by taking a matchup between Himawari SST hourly data and in-situ temperature observations. We then created daily Himawari SST by taking the daily average of the collected hourly data, and the created daily Himawari SST are used for the data assimilation. And this slide summarizes the setting of data assimilation experiment we conducted. The experiments were performed using the present JMA's Fodiva system for the North Pacific. The period of the experiment is from January to the beginning of July 2016. The assimilation window is set to 10 days, and assimilated observations other than SST along track sea level anomalies derived from JSON to Cryosat and Arctica, and in-situ temperature and salinity profiles. And we conducted 3 experiments. The control experiments was conducted under the same condition as the present operational system. That is, the Fodiva is based on the original version method, and the 10-day mean of MGD-SST is assimilated. And in old HIM experiment, SST data is replaced by Himawari SST, and it is assimilated with the original version of the Fodiva method. In the third experiment of new HIM experiment, Himawari SST is assimilated using the newly developed Fodiva scheme. In the new scheme, daily SST increments are optimized as well as increments to the initial condition. But as you know, the mixed layer depths in winter reaches a few hundred meters in the western North Pacific around Japan. So the SSD increments are projected down to mixed layer depths according to this profile in this experiment. So first, in the next slide, first we compare old heme and new heme experiment to see the impact of the new scheme. Here we look at the behavior of the cost function in the first 7 assimilation cycles. The left panel shows the value of the cost function, and the right shows its gradient. Red curve shows the new heme result, and the black curve shows the old heme result. And again, it should be noted that the same observations are simulated in old heme and new heme experiment. And you see that the cost function and its gradient in new heme shown by red curve decrease rapidly with iterations, while their decreasing rate in old heme are obviously slow. This is because short-term variations in Himawari SSD are well represented by the newly added daily SSD increments in new heme experiment. But the short-term variations are not controlled by increment to the initial condition in old heme experiment. Actually, if we compare SSD time series of the two experiments and Himawari SSD observation at the specific point, you see that the SSD in new heme shown by red curve will represent the short-term variations in Himawari SSD shown by this blue curve. In contrast, there are some discrepancies between old heme results shown by black and the observation. So these results indicate that the new scheme works quite well. Next, we evaluate SSD RMSE, which is calculated against in-situ temperature observations. Here we use fast vs SSD instead of SSD analysis because the observations used for the RMSE calculation were also assimilated. The left is control and the right is new heme result, and the background contour indicate mean SSD. You see that the RMSE is relatively large in SSD frontal regions, such as around the Kuroshio Current and the region east of Japan. And we then take the difference between them. So this figure shows the control minus new heme RMSE. So red color indicates RMSE reduction in new heme experiment. You see that RMSE for new heme are improved in most areas of the western North Pacific region. So finally, we look at impacts on subsurface temperature. This figure shows vertical profiles of temperature RMSE calculated over the western North Pacific region. Black is control, red and blue show new heme and old heme. So if we compare between new heme and control, black and red, Improvements in RMSE for new heme are seen up to around 150 meter depths. In contrast, in old heme experiments, shown by blue curve, subsurface temperature is degraded compared to control experiment. This is probably because the slow convergence of the cost function lead to the degradation of the analysis field in old heme experiment. So in summary, we have developed a new Fujii scheme based on weak constraint Fujii to assimilate high-resolution SSD. In the new Fujii scheme, daily SSD increments are added to control variables to represent short-term variations. The results of assimilation experiments suggest that the new scheme works quite well and short-term variations in Himawari SSD are well represented. For the future work, we will need further evaluation of the new scheme with longer assimilation experiments. And we will also need tuning or optimization of assimilation parameters such as observation errors for Himawari SSD, background error for SSD, and vertical projection coefficient profile of SSD increments. So that's all. Thank you for listening.